Hello, and welcome to Physics for Play. In today's video, we will be exploring how to do the Taylor series using Mathematica's series command, and we'll explore a couple of different examples using it. Let's get started. So last time, we talked about why the Taylor series is incredibly important in physics and how it shows up everywhere. This time, we're going to go through a little bit of the mathematics of it using Mathematica. So it turns out that, like most things, Mathematica has some convenient commands that allow you to write Taylor series very easily. The command is just series. I'm going to write the series expansion for some function f of y. And I am going to do that around the point y equals 0. And I'm going to do, let's start off doing it to second order. You can see it is just the equation we wrote down originally in the last presentation. You approximate f of y near 0 as being f of 0 plus the first derivative at 0 times y plus 1/2 the second derivative times y squared, etc., etc. We can, of course, expand this to an arbitrarily large number of higher order terms. We can truncate it wherever we like. We can also, we do not have to expand it around y equals 0. We could expand it around some other value. I'm going to say expand around y equals a. The difference, as you'll see, is now it's not going to be f of a that f of 0 I plug in here. I'm going to be approximating it near the point a. So I'm going to plug in f of a. Similarly, it'll be f prime of a, and the factor you multiply by is no longer y. It's going to be y minus a. So that when you plug in y equals a, all of these higher order terms go to 0, and you're just left with f of a. So that's great. Mathematica gives us an easy way to take series expansions. Let's show some practical examples of that. So let's do the series expansion for the gravitational force, which is equal to minus g times the, let me actually put that in the right spot, g times mass of the Earth times the mass of the object feeling the force of attraction to the Earth, divided by r squared. So that's Newton's famous 1 over r squared law. We're going to expand that with respect to r near the radius of the Earth. Now I'm going to do, we'll do it near the radius of the Earth. And I'm going to do that to first order. So we'll just include the first order correction. And you'll see that here. So we've got minus g mm over radius of the Earth squared. And then we got this first order correction. This is the first thing that'll have the variable r in it. Otherwise, it's just a constant. Now, as we mentioned last time, this constant is just m little g, where little g is the 9.8 meters per second squared that you measure in intro physics. And we can show that by actually plugging numbers in. And Mathematica also convenient because we can just ask it what the value of certain constants are. So I can have it spit out the gravitational, the gravitation constant value. I can have it spit out the mass of the Earth, and which is close to 6 times 10 to the 24 kilograms. And I can have it spit out the radius of the Earth. That's going to be in miles. I'm going to want it in meters. So I can tell it, give me the radius of the Earth in meters. And I can just copy these down. So I can copy all of these. I'm gonna cheat because I've done this beforehand. So I'm just gonna copy and paste these values in. and you can confirm that they match up. There might be a few more digits of precision in some of these. But once I do this, I can just plug that in. I can say G is going to be equal to the series expansion. Actually, let me be a little bit lazy and copy this. G is going to be equal to the series expansion of these values approximated near radius of the Earth, and we'll go out to second order or to first order. If I plug that in, you can see. Oh, let's just do this for. Let's do the acceleration of gravity rather than the force, so I don't have to worry about making up a mass there. And you can see you get your familiar 9.8 meters per second squared, and you also get a first order correction. If you want to, so r is the distance from the center of the Earth. If we want to be a little bit fancier, we could make this how high off the ground you are, because that's more likely what you are to measure. So we'll approximate x as, nope, this should be a plus sign. We'll approximate it at x equals 0. So at x equals 0, I plug in 0 for here, and I just get r as the radius of the Earth. If I do that, it turns out to be a little bit nicer. You've got just that cofactor in front of the x. You don't have to worry about the radius of the Earth showing up in your equation. Okay, so that's a fun example involving gravity. Up next, I want to talk about the Leonard-Jones potential. And the Leonard-Jones potential is frequently used to model molecular and intermolecular forces. So the Leonard-Jones potential looks like this. VLJ as a function of the, so this is the potential energy between, let's say, two atoms or molecules as a function of the distance between them. And we're going to write that as 4 epsilon times minus, or not minus yet, we'll do sigma over r, and we're going to take that to the 12th power. And then we also have, and we'll plot this so you'll see what it looks like. Then we also have another term that is sigma over r to the 6th power. And you can think of sigma, you can see it has units of distance. So you can think of sigma as being kind of like the radius of the molecular atom, and epsilon as being the bonding strength. So for convenience, I'm going to plug in epsilon equals 1. I'll plug in sigma equals 1. And we'll go ahead and we will plot that potential. So this is the potential energy as a function of distance. So we're going to go ahead and plot VLJ of R. For R goes from, you can play around with these parameters, but it gets big very quickly. So there's kind of a tight range you want to look at. We're going to go from 0.85 to 2. And I'm going to make my plot range go from -1 to 1, so I don't have to worry about the potential getting really big and swamping out what my graph looks like. And I'll put an axes label in. Not what I want. This will be the separation R. And then the next term will be the Leonard-Jones potential. By the way, if you might think that Leonard-Jones were two guys, or two people that came up with an energy equation that they called Leonard-Jones, and maybe they argued over who got the credit. But I'm told that Leonard-Jones is actually one person. with a hyphenated name. So here's what you see. You see that if I try to smush, if I try to compress the two molecules together, if I try to compress them beyond their spacing, beyond their size, so below 1, that gives you a really big energy and it shoots up. And in fact, if I expand this, you can see it shoots up quite rapidly. But then there's some binding energy, which in this case we set equal to -1. That was the epsilon value we set here. That's the strength. So you have a well of depth 1. And then the further and further away you get, if I go out to 100, you see this. I don't even have to go out to 100. If I go out to about 10, you can see this flattens out. And all of a sudden there's no, for any separation that's anything after 3 or 4, you pretty much have no potential energy. It's just you've got some binding energy. Binding energies are always negative. You got some binding energy that is in the 1 to 2 units of distance separation here. Okay, so that's the Leonard-Jones potential, but what the heck does this have to do with a Taylor series? This is not a polynomial expansion. Well, what we can do is we can model this as a harmonic spring if we want to approximate the potential, make it easier to calculate, easier to do theory with. And to do that, we want to approximate near the bottom of this well. So we got to find the minimum of that. So let's go ahead and minimize that function. We'll minimize VLJ, the Leonard-Jones potential, using the Mathematica command minimize. And I don't need a list here. I'm going to minimize this with respect to R. You can see that you get a negative value here. That's because this function is symmetric around the y-axis. But I can tell that I'm only looking for minima in the positive reals. Positive reals. Helps if I spell it right. And then it'll give me 2 to the 1/6, which if I want to know the numerical value of that, I can just throw a decimal point in there. And it's this minimum occurs around 1.12, which if you look at our chart, you can see that minimum occurs roughly in that 1.12 area. Okay, so that is my minimum value. So I'm going to set Rmin equal to that. So that is where the bond is most stable. And I am going to go ahead, now I'm going to do my Taylor series. I'm going to expand VLJ as a function of R around the point Rmin, and we'll go to second order and see what that looks like. You can see you get a form that looks like this. So what I can do, let me just plot that second order series expansion along with that. So I'm just going to copy everything up to the higher order terms here. We'll plot the original potential, and we'll plot the approximation. I'll put in a legend, and we'll say the first thing we're plotting is the Leonard-Jones potential, and then then we'll plug in the harmonic approximation. And you can see, now the reason we call this a harmonic approximation is because remember, a simple harmonic oscillator, the energy of a simple harmonic oscillator goes as x squared. This also goes as the distance squared. So we have the same type of potential energy in this approximation as we would for a simple harmonic oscillator. This is one of the reasons why we can approximate molecular bonds as being kind of like springs, because for small deviations from the, for small perturbations around the minimum of that potential for small amounts of energy, vibrational energy, it's going to be well approximated by this harmonic function, basically in the area where the orange overlaps the blue, right at the bottom there. We can also, I'll try to do this, we can also plot the force. So I am going to plot the force here. Now remember, you may recall that the force is minus the derivative of the potential. So I can, again, Mathematica is your friend. You don't have to do all of this computation by hand. We're just going to plot the force here. I'm actually going to expand my my plot range here because I want to see, let me just do plot range goes to all to make sure we get it all in there. And I'm gonna change my range a little bit because it's gonna blow up if I get too far below 1. So we'll do 1.05 to 2. Oh, and I got to change this because this is no longer the potential we're plotting. This is the force, and I probably don't need a plot legend. So what does this mean? Let me actually change my range here. We'll go to 1.5. Nope, no, go back. What does all this mean? Well, at the minimum of the potential, right at the bottom of that well, which again occurred at a position around, no, that's not what I want. Occurred around 1.12. So at the bottom of this well, there's no force. If the bond is stretched that length, you have no force, which means the force is going to be 0 at that value, just a little bit bigger than, just a little beyond 1.1. If you compress the molecular bond, so you try to make it smaller than it wants to be. Again, this is the rest length of that bond. This is the length it wants to be. If you compress it, so you move in the negative direction on the x-axis, you very quickly get a big force. The force gets blows up. If I were to plot this for an even smaller range, you can see two molecules really don't want to be on top of each other. So they push back with a really big positive force, trying to make that separation bigger. On the other hand, if you were to stretch the bond, make it larger than it wants to be. So I stretch it, I move in the positive direction in the separation. This is the separation of the two molecules that are feeling the force. What you will see is that force pushes back, but not nearly as much as if I tried to put the two molecules on top of each other. So there will be a negative force, because this crosses below the x-axis. You're going to have a negative force trying to compress you back to be the rest length of the bond. But you will see as we go out a large distance, that force just goes to 0. So eventually, if I pull two molecules far apart, I break the bond is no longer there. There's no more force to pull back with. Just as we did with the potential, I can do a Taylor series of that force. So I can say, give me the series expansion of the force, which again is minus the derivative of the potential. And we're going to do that for R goes from, where do I want to, I want to expand around the minimum of the well. So the place where the force is equal to 0, and we'll expand to first order. You get something that looks like this. You got a first order function. It looks a little bit nasty because I didn't plug decimal numbers in here. Mathematica is trying to hold all the precision by giving me exponents to the 1/6 and 2/3 power. But I can just copy that up to, so we're just copying everything up to second order. as our approximation. So this would be like, this will give me what the Hooke's law force looks like. So I should return my plot legend in here. And let me actually give this a range, because I do not want to see everything here. I need to make the range a bit bigger and maybe a bit smaller. And let's actually go over a shorter. There we go. So what you can see is that you've got something that is a Leonard-Jones force. That's this blue curve here. It is not a Hooke's law force. So remember, Hooke's law was just a straight line. And an actual molecular bond is not going to be that, but I can approximate it as that as long as I don't stray too far from the equilibrium position. As long as I don't stray too far from the natural bond length. So anything in this range, so very small stretching, we can approximate pretty well where this orange curve, the harmonic approximation, and the original potential overlap. So for small deviations from that rest bond length, this is a good approximation. So hopefully this gives you a flavor for some of the types of things that you can do with a Taylor series, how you can make approximations for different physical systems. We'll actually show you how you can model things like molecular bonds a little bit later in this video series, how you can model it using the Leonard-Jones potential when we get to anharmonic oscillations. But we're going to save that for another time. We're going to stop here, though. Go ahead and like the video if you liked it. And if you'd like to see more of these, please click subscribe.